A faint tremor in the fabric of starlight was all it took to change the direction of an entire field of science. It began as a whisper, barely detectable, almost dismissible. A thin, wavering dip in a spectrum captured by JWST as it drifted in silent vigilance beyond the moon's shadow. The signal did not shout. It called gently, like a distant ripple brushing against the hull of a ship on a vast, unseen ocean. Scientists stared at it, unsure if their eyes were playing tricks. But the whisper persisted, steady, rhythmic, true. Light, after all, carries secrets. It holds the histories of stars, the scars of worlds, the breath of atmospheres. JWST, with its mirrors unfolded like a celestial lotus, had been built to hear the faintest of these secrets, to translate darkness into meaning. And in that single observation window, on a world orbiting a dim and relatively unremarkable star only 26 light-years away, the telescope seemed to capture something alive. A spectral signature that hinted at water vapor, one of the most precious and temperamental elements in the universe. The silence surrounding the data was almost eerie. Space itself contributes nothing but stillness. No wind, no rustling, no ambient hum. Only light moves, only light speaks. And yet within this quiet, the signal seemed to pulse with a kind of urgency, as if the universe had slipped an encrypted message into humanity's waiting hands. Across the control rooms, researchers leaned closer to their screens, breath tightening, pulse quickening. Because water is never just water. When found in the right place, at the right temperature, wrapped in the right atmosphere, it becomes a whisper of something far bigger. The world in question was small, lost in the glow of its star, a mere silhouette gliding across the stellar face. JWST detected it not by sight, but by shadow, by how starlight filtered around it, through it, across whatever gases may cling to its surface. Such observations are delicate. A slight error in calibration can distort the truth. A stray cosmic ray can imitate a meaningful spike. Data analysts know better than to trust a single hint of hope. And yet, the signal was unmistakable. There, within the spectrum, lay the unmistakable bending of light caused by water vapor molecules. But mystery is not content with simple discovery. It demands more. As the team dug deeper, the questions multiplied. Was the signal a fluke? Was the planet's atmosphere thick or thin? Was the water abundant or fleeting? Had they glimpsed clouds, steam, or a chemical imposter wearing a watery disguise? The universe loves ambiguity. It has never promised us clarity. It offers instead the allure of the unknown, daring us to look closer, think harder, reach further. The cosmic backdrop against which this discovery unfolded only intensified the wonder. Imagine the planet's world, its skies tinted by the color of its star, its horizons stretched beneath a faint glow that never quite resembles daylight. Perhaps it is a warm world, wrapped in the heavy breath of vaporous air. Or perhaps it is cold, its water locked away in icy layers that release faint vapor plumes only when warmed by starlight during transit. JWST cannot show us the surface. It can only trace the outline of its secrets like a blind hand pressed against an unseen door. Still, something about the signal felt deliberate. Not in an artificial sense, but in the sense that the universe had waited long enough. Humanity has wandered for thousands of years, scanning the heavens with glass lenses, radio dishes, and equations sketched in notebooks. And now, with JWST, we finally possess an instrument capable of catching the faintest chemical size from distant worlds. If there was ever a moment for the cosmos to reveal a tantalizing clue, this felt like it. As the spectral lines were plotted again and again, the sense of impending revelation grew heavier. This was not a detection from billions of years ago, from galaxies formed when Earth itself was little more than cooling rock. This signal was from our neighborhood, cosmically speaking, from a place we could one day visit, map, or send robotic scouts to. 26 light-years is far in human terms, but stunningly close in cosmic terms. If water existed here, then how many more worlds like it drift in the nearby dark? Night deepened across the Earth as scientists in different time zones picked up the data. The signal seemed to echo across continents, whispered from lab to lab, office to office. Each researcher brought their own hopes and fears to the interpretation. Some felt the rising thrill of possibility, that this was the first piece of evidence pointing toward a cluster of habitable worlds scattered near our solar system. Others approached with caution, aware that science punishes premature excitement. Yet all agreed. The universe had given them something real, something undeniable, something worth chasing. In this moment, humanity stood at a threshold. A single spectral feature had opened a door, not fully, but enough to let a crack of light spill through. Enough to remind us that while we drift on a small blue sphere in a vast, indifferent void, the void may not be as empty as we once believed. And so the whisper continued, faint but insistent, carried across the vacuum through particles of light older than our species. The discovery did not promise answers. Promise questions, deeper, sharper, more unsettling questions. Ones that would pull scientists into new missions, new debates, new observations. Because if water could exist there, then life could too. And if life could exist 26 light-years away, then perhaps we have never truly been alone, only unaware. The cosmic whisper lingered, neither confirming nor denying anything. But it had spoken, and humanity, for the first time in ages, felt the universe whisper back. Time itself behaves strangely when observed through the eyes of a machine built to chase ancient light. JWST does not merely look through space. It looks through history, peeling back the layers of cosmic time the way archaeologists brush aside dust to reveal forgotten civilizations. When its gold-plated mirrors align, they reach across billions of years, gathering photons that began their journey long before Earth had oceans, continents, or life. To observe with JWST is to witness the universe as it once was, a silent film projected across the abyss, the frames composed of infrared wavelengths too faint for human senses to grasp. The telescope was designed with a single obsession, to see what could not be seen before. Where optical telescopes reveal bright stars and glowing galaxies, JWST pierces into the hidden spaces between them. The dusty nurseries where stars are born, the veiled atmospheres of distant planets, the faint radiation left behind by cosmic events that reshaped everything. Infrared light behaves like a cosmic key, slipping through clouds of dust that would suffocate visible light, unlocking rooms in the universe we never knew existed. Every time JWST orients itself toward a target, it is preparing to unwrap another layer of the universe's secrets. The engineering alone feels almost supernatural. To function, the telescope must remain impossibly cold, shielded from the sun, Earth, and Moon by a massive layered sunshield stretched as thin as a razor and wide as a tennis court. This shield, shimmering like a silver sail in the darkness, blocks heat with a precision that borders on absurd. One side faces the sun and sizzles hotter than boiling water. The other sinks to temperatures colder than Pluto's shadowed craters. Between these extremes, the telescope maintains a delicate equilibrium, an oasis of cold stability where ancient photons can be captured unwarped and unspoiled. Its mirrors, 18 hexagonal segments, reflect light with almost unnatural perfection. Each segment is made of beryllium, polished so precisely that if scaled to the size of Earth, the tallest imperfection would measure less than the height of a human hair. These mirrors fold open in the void like petals, locking into place with quiet determination. Together, they form a golden eye capable of detecting the faint thermal breath of stars forming in distant galaxies, or the subtle cooling of matter collapsing into black holes. Every reflection inside JWST is a conversation with time. For scientists, working with JWST's data is akin to reading confessions written by the universe itself. The signals it captures are delicate streams of photons, filtered and decoded through instruments designed to separate wavelengths into thin, colorful threads. Each thread contains a signature, chemical, thermal, structural, that maps the story of what the light passed through on its way to us. Sometimes the story is violent, carved by supernova explosions or stellar winds. Other times, it is gentle. The soft glow of a newborn star nestled in a nebula, or the faint dimming of starlight as a small planet crosses in front of its parent star. Yet the telescope does more than observe distant epochs. It challenges our understanding of existence by revealing that the past, present, and future are not neatly separated. When JWST looks at galaxies formed shortly after the Big Bang, those galaxies appear young, chaotic, and raw, even though they are older than the Earth itself. When it studies exoplanets only a few dozen light-years away, the light might be from just 26 years ago. In cosmic terms, that is practically yesterday. JWST creates a strange duality, a tool that can summon the earliest moments of creation and simultaneously examine worlds close enough to imagine visiting. The telescope blurs the line between myth and reality. Its discoveries arrive with a sense of cinematic drama. A single observation window might reveal a swirling galaxy whose light began its journey when early humans first discovered fire. Another might show the pale outline of a planet passing in front of a dim, quiet star in our galactic neighborhood. This blending of the ancient and the nearby gives JWST a unique storytelling voice. It speaks in contradictions. The universe is unimaginably vast yet intimately connected, overwhelmingly old yet constantly renewing itself. It invites us to step into the role of cosmic witnesses, compelled to decipher messages written across the sky. The journey of light across time is more than a scientific concept. It is a reminder of how fragile our presence in the universe truly is. While JWST studies ancient galaxies, Earth continues its orbit around the Sun. Humanity continues its restless search for meaning, and time marches on for us at a pace we can feel. But the telescope, suspended in cold space, feels no such urgency. It measures time in wavelengths and redshifts, in the quiet hum of instruments calibrating themselves in the darkness. Its world is timeless, governed by the rhythm of photons rather than the heartbeat of human civilization. And yet, for all its precision and cold detachment, the telescope inspires deep emotional reactions. When researchers first saw the high-resolution images of the Carina Nebula, many felt tears welling as cosmic dust pillars, once blurry shadows, became intricate cathedrals of gas and starlight. When JWST captured galaxies warped and stretched by gravitational lensing, astronomers felt a mixture of awe and fear, realizing how much of the universe remained hidden behind veils of invisible matter. Each new dataset is a reminder that the universe is far stranger than our ancestors could have imagined, and far more beautiful than any myth ever described. The more JWST observes, the more it shifts the philosophical center of gravity. Humanity once believed the universe revolved around Earth. Then we learned the Sun, not Earth, was central to our solar system. Later, we discovered that our solar system was only one among billions in a galaxy of stars. Now, JWST forces us to confront another unsettling truth. The universe is filled with worlds that may host oceans, clouds, storms, and perhaps even life. The telescope turns the night sky from a distant, decorative ceiling into a map of potential neighbors. But for all its power, JWST is humbled by the universe's enormity. There are observations it cannot make, wavelengths it cannot reach, distances too great even for its sensitive instruments. Each discovery is also a reminder of limitations, gaps in our understanding that beg for even more powerful telescopes, faster probes, deeper theories. JWST stands as both a triumph of human ingenuity and a promise that our search has only begun. As it stares into the darkness, the telescope becomes something more than a machine. It becomes a time bridge, an instrument that connects our present moment to the universe's distant past, inviting us to contemplate the cosmic timeline on which we exist. It shows us that the stars are not just points of light but chapters in a story billions of years old. And with each new observation, JWST pushes us one step further toward understanding where we came from, where we are, and what might be waiting for us in the places we have yet to explore. In the quiet expanse where the telescope floats, shielded from sunlight and the noise of Earth, it continues to listen to the universe's faintest murmurs. Every photon it captures is a message from another era, a fragment of time preserved in light. As these photons accumulate, a mosaic of cosmic truth slowly forms, one that will redefine our place in the universe. And through this golden mirror, humanity glimpses not just distant stars but the staggering depth of its own curiosity, stretching endlessly toward the unknown. The space just beyond our sun is not empty. It is a vast and intricate wilderness of drifting stars, wandering planets, rogue worlds, and dormant comets. An enormous cosmic neighborhood that humanity has barely begun to map. When we imagine the universe, we often jump to far-off galaxies or ancient cosmic explosions, but the true frontier lies closer, in the dark, silent pockets between the stars nearest to us. These nearby systems are like islands scattered across a black ocean, each carrying its own climate, chemistry, and mysteries waiting to be uncovered. And because of their proximity, they form the most promising stage on which the story of life beyond Earth might unfold. Within about 50 light-years of our solar system lies a cluster of stars. Some bright, some dim, some young and reckless, others old and quiet. These stellar neighbors are not aligned neatly or arranged according to any pattern we can easily predict. Instead, they float in a slow, eternal drift, each following its own orbit around the galactic center. Their distances from one another seem immense, yet compared to the scale of the Milky Way, they are practically next door. When JWST investigates a star system only 26 light-years away, it is observing a place so close that its light left when many people alive today were already children. We often picture our sun as the standard model of a star, but across this neighborhood, the sun is only one example among many. Some nearby stars burn hotter and brighter, their surfaces boiling in intense blue-white fury. Others are tiny red dwarfs, so dim that a human eye could never detect them even from relatively short distances in space. Red dwarfs produce flares powerful enough to scorch their planets, and yet they are abundant, far more common than sun-like stars. Many of the most intriguing exoplanets orbit these small, temperamental stars, including the world where JWST recently detected water vapor. The arrangement of nearby stars creates a strange and beautiful sense of scale. Imagine drifting between these systems, the sun shrinking behind you as another star begins to glow ahead, like a distant lantern guiding a traveler across lonely waters. The constellations would distort and warp, their shapes unraveling into unfamiliar patterns as your vantage point shifted. Space itself would remain dark and vast, yet the presence of another star so close would make the void feel less empty, as if stepping into another room of the same grand mansion. Some of these stars form binary or even trinary systems, multiple suns locked in gravitational ballet. A planet in such a system might see 2 or 3 sunsets each day, its skies painted with layered shadows and braided beams of light. Others orbit solitary stars in quiet stability, worlds where day and night follow predictable rhythms over billions of years. Still others drift free, unbound by any star at all, condemned to wander in perpetual darkness. Our local cosmic neighborhood is not uniform. It is a patchwork of environments, each shaped by the temperament of its central star. The star hosting the newly observed exoplanet is faint and unassuming, the kind you might overlook without realizing how much power and story it holds. It emits a soft glow, its light stretching across space like a muted beacon. To JWST, however, even this quiet star provides enough illumination to study the thin halo of gases surrounding its orbiting planet. The star's radiation interacts with the atmosphere, sculpting it, heating it, shaping its chemistry. In the spectral lines, the planet's silhouette appears like a shadow drifting across a cosmic spotlight, its atmosphere etched into the light that reaches us. In many ways, our solar system is not typical. We have a gas giant far from the sun, a habitable world with liquid oceans, and smaller rocky planets arranged in an elegant progression. But nearby systems show a staggering diversity. Some planets cling so close to their stars that they complete an orbit in mere days, their surfaces scorched and molten. Others circle in wide elliptical paths, experiencing seasons that last decades. And then there are planets whose orbits suggest chaotic histories, collisions, migrations, gravitational battles long since ended. These worlds are like characters in a cosmic novel, each shaped by forces older and more violent than anything we experience on Earth. Their atmospheres whisper stories of formation, erosion, volcanic fury, and meteor impacts. Their surfaces, though unseen, might hold frozen plains, boiling lakes, glassy deserts, or cloud-shrouded oceans. The closer these systems are to us, the more their stories matter. Because if life emerged in more than one place in our galactic neighborhood, it changes everything about how we view our own origins. Standing on Earth, we often forget that the stars are not just points of light. They are places. Real, physical locations with weather, climates, storms, and chemical reactions unfolding in real time. The exoplanet JWST has studied is one such place. Small, distant, unseen, yet undeniably real. It circles its star in a rhythm older than our species, its atmosphere rising and falling with each transit, its chemical identity briefly illuminated as starlight filters through its sky. What makes nearby systems so compelling is the possibility of future exploration. With current technology, sending probes to such distances is not yet possible, but it no longer feels like a fantasy. 26 light-years is impossibly far for us today, yet unimaginably close relative to the size of the Milky Way. If humanity ever learns to travel between stars, or even send robotic emissaries capable of surviving the journey, these nearby systems will be the first targets. We imagine telescopes and sensors drifting past alien planets, reading their atmospheres up close, capturing images of surfaces shaped by forces we barely understand. These thoughts stir something deep within us, because the search for neighbors is also the search for belonging. Each nearby star we study expands our awareness, reminding us that the universe is not a cold, empty backdrop but a sprawling landscape filled with potential homes, potential histories, potential life. The systems nearest to us become mirrors through which we examine our own place in the cosmos. They show us how fragile our assumptions are and how vast our possibilities may be. The exoplanet where JWST found hints of water belongs to this intimate circle of stars, a world close enough to feel familiar yet distant enough to remain cloaked in mystery. Its discovery invites us to rethink what it means to be part of a galactic neighborhood. For the first time, the worlds next door are beginning to speak, revealing themselves not as abstract data points, but as living chapters in the unfolding story of the universe. And as we uncover more about them, the boundary between imagination and reality grows thinner, drawing us deeper into the cosmic ocean that surrounds us. The planet revealed itself not through a photograph or a distant glimmer, but through a shadow, an elegant, almost ghostly silhouette carved into the light of its star. It moves quietly, faithfully, in a path it has traced for millions of years, orbiting a dim red dwarf that burns with a soft but relentless glow. To the naked eye, the planet is invisible. To even the most powerful optical telescopes, it is nothing more than blended darkness. But to JWST, it becomes a presence, a subtle distortion in starlight, a shifting pattern, a world outlined not by shape but by the whisper of its atmosphere. It is a world hidden in the star's radiance, a planet in the shadows. Every time it crosses its star's face, a fraction of starlight bends around it, passing through whatever thin or thick gases might cling to its surface. In those fleeting moments, JWST captures the planet's fingerprint, a delicate spectral trace that reveals the molecules drifting in its skies. This world does not introduce itself all at once. It reveals itself slowly, layer by layer, like an ancient artifact being brushed free of dust. Its orbit is tight, closer to its star than Mercury is to the Sun, yet because the star is cooler and dimmer, the planet may not be scorched. Instead, it could be locked in a gravitational embrace known as tidal locking, with one side forever turned toward the star and the other plunged into endless night. Across the terminator line, the boundary between day and night, there may be a zone of balance, a twilight ring where temperature and chemistry take on their most intriguing forms. This narrow region, neither too hot nor too cold, could harbor conditions that surprise even scientists who have spent decades studying exoplanets. The star itself casts a reddish glow onto the planet's day side, bathing it in constant, muted light. The surface, if it has one, might be carved with shadows as long and sharp as blades, interrupted by regions that simmer under relentless heat. The night side, meanwhile, could be a place of frozen winds and dark horizons. In that eternal darkness, any atmosphere might condense, forming alien weather cycles entirely unlike Earth's. Storms could migrate across the twilight zone, driven by the temperature imbalance between the two hemispheres. Clouds could gather, disperse, and reform as the planet performs its ceaseless, synchronized dance around the star. Scientists do not yet know whether the planet is rocky or gaseous. Some models suggest a water-rich world, a mini-Neptune stripped of some of its gases, leaving behind thick clouds and deep oceans hidden beneath steam. Others propose a rocky super-Earth cloaked in vapor, with volcanic fissures breathing gases into the sky. If it is a rocky world, its landscape might be sculpted by forces both familiar and alien. Molten plains cooled into obsidian deserts, icy cliffs where night reigns eternal, or entire regions wrapped in fog-like mists rising from warm substellar seas. And yet, there is an unsettling possibility that deepens the mystery. The planet may not be alone. A spectral shift detected during one of the transit observations hinted at gravitational influence, too subtle to identify, yet suggestive of another body nearby. Perhaps a second planet shares the system, orbiting farther out in colder pastures. Perhaps a moon, large enough to pull gently on the planet's motion, circles unseen. Or perhaps debris, leftovers from ancient collisions, drifts in the planetary system like ghosts of a violent past. The shadows in the data raise more questions than they answer, and each unanswered question fuels the growing sense of cosmic intrigue. The planet's atmospheric signature is faint, almost shy. It tells us there is something there, molecules suspended in the air, but it does not yet tell us how deep, how complex, or how stable that atmosphere is. Does it wrap the planet like a warm blanket, protecting it from stellar flares? Or is it thin and fragile, vulnerable to the star's unpredictable bursts of radiation? In red dwarf systems, these flares can be catastrophic, but they can also drive atmospheric chemistry, creating complex molecules that might someday lead to life or mimic its presence. Every transit brings a sliver of new information, a fresh clue to the planet's identity. But each transit also reminds us how much remains hidden. JWST catches only a glimpse, a narrow window of a few hours, while the planet continues its orbit in secrecy. If the atmosphere is thick, it could distort the starlight in ways that mask certain chemicals. If clouds swirl across its skies, they could obscure the deeper layers from view. Even the presence of water vapor, if confirmed, would raise more questions than it answers. Is the water part of a global system, cycling between vapor, liquid, and ice? Or is it trapped in the upper atmosphere, evaporating from a surface too hot or too volatile to sustain anything stable? As scientists stare at the data, the planet becomes more like a riddle carved into the cosmos. Everything about it invites interpretation, speculation, and wonder. It is neither clearly hospitable nor clearly barren, neither welcoming nor hostile. It exists in that perfect tension where imagination and science collide. A place where life could hide or where chemistry could mimic life signals. A world that seems familiar at first glance but grows stranger the closer we look. In the end, the planet remains a silhouette, a shadow moving across a dim red star, carrying secrets wrapped in vapor and heat. It drifts in the cosmic night, neither calling to us nor avoiding us, simply following its ancient course as it has since long before humans evolved. And yet, through the eyes of JWST, it now occupies a place in our story. It becomes a destination for future questions, future missions, future hope. A planet in the shadows, quiet, distant, mysterious, holding within its silent orbit the possibility that we are on the edge of discovering more than we ever expected. Light is more than illumination. It is a messenger, a traveler, a silent archivist carrying the memories of everything it touches. When JWST studies an exoplanet, it does not rely on images or direct views. Instead, it listens to light itself, specifically, to how that light changes color as it filters through an alien atmosphere. This technique, known as spectroscopy, transforms invisible wavelengths into a readable language. Through it, scientists can decode the chemical story of a world they will never physically see, using nothing more than the faintest shifts in starlight. Imagine holding a prism up to a beam of sunlight. The light splits into a rainbow, each color representing a wavelength. Now imagine that same rainbow arriving from a distant star, and a planet drifting between the star and the telescope. As starlight passes through the planet's atmosphere, some wavelengths vanish, absorbed by molecules. Water vapor steals certain bands. Methane takes others. Carbon dioxide carves its own unique notches. Each molecule leaves behind a missing line, like a secret carved into the spectrum. These missing lines are the planet's fingerprint, its chemical signature, invisible to our eyes but unmistakable to a machine built to detect them. JWST's instruments do not see colors the way humans do. To them, light is a coded sequence of peaks and dips, a map of absorption patterns spread across infrared wavelengths. When plotted, the spectrum resembles a mountain range, with valleys carved where molecules have absorbed the light. Scientists scan these features as though examining ancient inscriptions, searching for patterns that align with known molecular signatures. It is a meticulous process, requiring sensitivity capable of detecting changes in brightness smaller than 1 part in 10,000. Yet within those tiny fluctuations lies the identity of an entire atmosphere. Infrared light plays a crucial role in this process. Unlike visible light, which can be stopped by dust or thick clouds, infrared wavelengths slide through obstacles with almost effortless grace. They pass through gases and vapors that would otherwise obscure the truth. This allows JWST to peer into layers of an atmosphere that telescopes before it could never reach. Pounds of gas, droplets of steam, wisps of cloud. Nothing escapes the scrutiny of infrared spectroscopy. It reveals what a planet breathes, how it evolves, what elements shape its climate, and even whether volcanic or chemical processes are at work beneath the clouds. But the true magic of spectroscopy lies in the tension between revelation and mystery. The technique reveals just enough to ignite curiosity, yet never enough to remove all uncertainty. When JWST identifies an absorption feature, it raises further questions. How thick is the atmosphere? Which layer did the light pass through? Were the molecules spread evenly or gathered in clouds? Were they affected by heat, frost, or stellar radiation? Each answer leads to new uncertainties, and each uncertainty pulls scientists deeper into the investigation. The act of reading spectra is like hearing a whisper from across an immense distance. Scientists lean in examining anomalies, dips where none should exist, curves that deviate from expectations, subtle distortions that hint at unknown chemistry. Light behaves with both precision and mischief. Tiny fluctuations could signal the presence of a rare molecule, or they could be nothing more than noise, an echo of the star's surface or a ripple in the telescope's machinery. Interpreting the difference requires experience, intuition, and patience. The complexity of the process becomes even more profound when clouds come into play. Clouds, whether of water, methane, or exotic chemicals, scatter light in unpredictable ways. They can flatten spectra, dilute signals, or mask entire chemical layers beneath a reflective haze. A world covered in clouds might hide oceans beneath them, yet the spectrum would resemble that of a barren, featureless planet. Conversely, a world with thin or patchy clouds might reveal faint hints of molecules that suggest something more dynamic. Spectroscopy becomes a delicate dance between discovery and uncertainty, a battle to extract truth from layers of atmospheric disguise. The exoplanet observed in this case revealed a spectrum filled with tantalizing features. JWST captured the starlight bending through its atmosphere, extracting faint patterns that seemed to align with water vapor signatures. But amidst the clarity were hints of something unexpected. A distortion here, an unusual dip there. Signals that could be clouds or chemical interactions or something more exotic. The spectrum seemed to hold its message tightly, offering glimpses but refusing to fully reveal its secrets. This moment of ambiguity is where the emotional power of spectroscopy lies. The universe rarely gives straightforward answers. Instead, it provides fragments, pieces of a puzzle meant to challenge humanity's hunger for understanding. Each spectral line becomes a narrative thread. Each dip becomes a clue. Each uncertainty becomes an invitation to look again. This tension between knowing and not knowing ignites a sense of wonder that transcends scientific analysis. In the end, spectroscopy does more than analyze the atmospheres of distant worlds. It transforms the universe into something intimate, something we can read, interpret, and emotionally connect with. It turns starlight into language, planets into characters, and cosmic distances into bridges of meaning. Through the prism of spectroscopy, invisible worlds become visible, silent worlds speak, and the universe reveals that even its faintest signals can carry profound truths. And so, the spectrum of this distant exoplanet hangs before us, part revelation, part enigma, challenging us to decipher the message hidden within its shifting colors, urging us deeper into the mystery that surrounds this world in the dark. The moment the data appeared on scientists' screens, a hush fell across the room, not of confusion, but of recognition. There, carved cleanly into the spectrum, was a pattern unlike the typical atmospheric noise that often muddles exoplanet readings. A dip in the infrared wavelengths, a curve that refused to flatten, a shape that matched simulations almost too perfectly. Water vapor. The signal wasn't loud or dramatic. It was precise, steady, confident. It struck scientists with a kind of electric stillness, the way a soft knock on a door can feel more startling than a thunderclap when no visitor is expected. The shock did not come from the idea of water alone. Humanity has detected water in many places: icy moons, comets, far-off nebulae, even the atmospheres of distant gas giants. But this time, the water signature came from a small world orbiting a star just 26 light-years away. It came from a planet that was not a gas giant but potentially rocky or ocean-rich, a planet whose size and temperature placed it tantalizingly close to the conditions we associate with habitability. The signal suggested the presence of water vapor drifting somewhere within its atmosphere, molecules illuminated by starlight in a fleeting alignment captured only because JWST happened to be watching at the perfect moment. The initial reaction among researchers was not celebration but disbelief. Teams from different institutions ran the data independently, hoping, almost expecting, to find an error. Perhaps an instrument artifact? A calibration misalignment? A flare from the host star? All these explanations were tested, cross-checked, and eliminated one by one. JWST's unprecedented sensitivity meant that it could separate a planet's atmospheric signature from the star's glare with astonishing precision. The water signal held steady through multiple analyses, refusing to vanish no matter how skeptically it was interrogated. It was not merely a hint, it was a declaration. As the magnitude of the detection settled in, an emotional ripple spread through the scientific community. Some felt exhilaration. Water vapor could mean clouds, weather, humidity cycles, processes that make a world dynamic rather than static. Others felt a more cautious wonder. Water does not guarantee life, but it opens the door to environments where chemistry becomes complex and self-organizing. Still others felt a quiet awe, realizing that this was the closest any telescope had come to reading the breath of a potentially habitable world near our cosmic doorstep. But the discovery also carried a deep sense of tension. Water can be deceptive. It can come from steam rising off a superheated surface, from ice sublimating in a thin atmosphere, from photochemical reactions that have nothing to do with oceans or rainfall. The presence of vapor tells us something profound but incomplete, a single piece of a puzzle with edges still hidden. Is the planet warm enough to sustain liquid water? Is the vapor trapped in the upper atmosphere? Or does it circulate across layers like Earth's hydrological cycle? Does the signal represent lush possibilities or an atmospheric illusion? Then came the moment that shifted everything, when computer models began aligning with the observed data. Several simulations showed that the water signature fit best with an atmosphere thick enough to support weather, clouds condensing and evaporating, circulation patterns driven by the star's heat. This did not confirm habitability, but it added weight to the idea that this planet was not a dry, barren rock. Instead, it might be active, evolving, shaped by temperature gradients that sculpt its skies into storms and vapor currents. The scientific excitement grew even deeper when researchers compared the water signal to those from other exoplanets. Most water detections came from giant, bloated worlds where vapor swirled in atmospheres thousands of kilometers deep. This signal was more subtle, suggesting a world far smaller, perhaps a mini-Neptune shedding its outer layers, or a super-Earth with a warm, cloud-laced sky. Either possibility carries radical implications for how common water-rich worlds might be in our part of the galaxy. Yet uncertainty remained a constant companion. The spectrum showed another detail, an odd flattening in certain wavelengths, that could indicate clouds thick enough to obscure deeper layers of the atmosphere. If clouds are present, they could be masking additional molecules, hiding clues that would reshape our interpretation. Clouds can make a planet look cooler than it is, or hotter, or more humid, or more desolate. They are both a veil and a storyteller. Their presence means complexity, and complexity means the planet's narrative is far from straightforward. As more scientists joined the analysis, conversations shifted from, "Is this water real?" to, "What does this water mean?" The tone in research rooms became more urgent, more charged. Suddenly, the planet was no longer just a spectral curve. It was a world with weather, chemistry, and perhaps even a delicate interplay between heat and cold across its orbit. A world that had moved from theoretical interest to a genuine candidate in the search for biosignatures. The implications spilled into philosophical territory. Water vapor on a nearby planet expands the boundaries of what feels possible within a human lifetime. It transforms the night sky from an abstract canvas into a landscape filled with potential neighbors. It hints that worlds capable of supporting the ingredients for life may not be rare, nor unreachable, nor confined to distant galaxies. They may be scattered throughout the quiet, dim starlight of our local cosmic district. But the moment that made researchers lean closer, the moment that thrilled and unsettled them in equal measure, came from a final realization. The water signal was strong enough to demand further investigation. It was not a ghost. It was not noise. It was not a misreading. It was an invitation to return, observe again, dig deeper. An invitation from a distant world whispering through starlight, offering its secrets not all at once but in fragments. Enough to intrigue, enough to provoke questions, enough to pull humanity closer to the possibility that life in the universe may not be an isolated miracle, but part of a much wider, richer cosmic tapestry. The water signal stood as both a discovery and a beginning, a doorway into a chapter of exploration that would define an era. A silent message carried across 26 light-years, urging us to look beyond our small world and imagine what stories might be unfolding on that distant, shadowed planet drifting around a quiet red star. Water is simple, 2 hydrogen atoms and 1 oxygen atom, but in the context of the cosmos, it becomes one of the most powerful forces shaping the destiny of worlds. It sculpts landscapes where none should exist, drives climates that can nurture or destroy, and leaves chemical footprints that hint at origins older than stars themselves. When scientists speak of water, they do not mean the familiar blue liquid we see on Earth. They mean a universal architect, a molecule that has shaped galaxies, carved icy moons, and silently woven itself into the chemistry of life wherever life has managed to appear. Its presence on a distant exoplanet, even as vapor, sends shockwaves through astronomy because water is both ordinary and miraculous. Abundant in the universe yet incredibly difficult to find in the right conditions for life. Imagine the early universe before stars formed. Hydrogen and helium drifted through endless darkness, waiting for gravity to sculpt them into the first radiant furnaces. When those primordial stars lived and died, they forged oxygen in their fiery cores, releasing it into space. Only then, millions of years later, could the universe begin to form its first molecules of water. These molecules clung to dust grains, froze onto comets, swirled into planetary disks. They rode the waves of star formation like seeds carried on cosmic winds, embedded in the architecture of new solar systems. In this way, water became one of the oldest storytellers in existence, carrying with it the memory of stars long gone. On planets, water behaves with transformative intent. When liquid, it sculpts continents, smooths stones, wears down mountains, and fills valleys with oceans that cradle chemistry. When vapor, it forms clouds that reflect light, moderate heat, and shape weather systems. When frozen, it becomes a shield, preserving landscapes beneath its crystalline layers. Water does not simply exist on a planet. It defines the planet's character. It determines whether energy flows freely or becomes trapped, whether climates stabilize or spiral into chaos, whether the seeds of biology are encouraged or smothered. The presence of water vapor on a nearby exoplanet means that some version of this cosmic choreography might be unfolding far beyond Earth. But water also thrives in environments we would never expect. On worlds far colder than Earth, water forms glaciers of impossible thickness, hiding entire oceans beneath layers of ice tens or hundreds of kilometers deep. In the scorched atmospheres of gas giants, water appears as high-altitude vapor, never touching a surface. Around young stars, water forms in hot jets of steam, blown outward by intense radiation. It cascades through space in comets and clumps inside molecular clouds. This versatility means that detecting water does not immediately imply habitability, but it does imply possibility. And possibility is what fuels the search for life. The exoplanet under observation seems to possess a kind of atmospheric dynamism hinted at by the water signal. Vapor requires heat, enough to lift water molecules into the sky, and heat implies active circulation patterns. The planet might host towering clouds shimmering in the red glow of its star, or thin layers of vapor drifting high above its surface. These vapors could originate from oceans, ice, volcanic activity, or atmospheric chemistry. Each possibility tells a different story. Oceans suggest stability and long-term climate cycles. Ice vapor hints at sublimation driven by stellar illumination. Volcanic vapor implies geological activity, a planet not quiet, but alive in its own way. Emotionally, water evokes something deeper in the human mind than most molecules. It is tied to comfort, survival, memory, and origin. We are, after all, beings born from water. For billions of years, Earth's oceans sheltered early life, allowing chemistry to experiment until complexity emerged. To find water on another world is to confront the possibility that somewhere, somehow, the same processes might be unfolding. It creates a bridge between worlds, a familiar thread linking alien environments to our own deep biological past. Even if life does not exist on that distant planet, the presence of water vapor suggests conditions under which life could arise now or in some distant future. Scientists also recognize the paradox of water in the cosmos. It is abundant and rare at the same time. Hydrogen is the most common element in the universe, and oxygen is forged readily in massive stars, making water one of the universe's easiest molecules to create. Yet liquid water, the form most associated with biology, requires almost impossibly precise temperature ranges. Too close to the star and it boils away. Too far and it freezes solid. Too much atmosphere and it becomes superheated. Too little and it escapes into space. Worlds must walk a narrow line to host stable water cycles, and this narrowness makes such worlds incredibly precious. Thus, the detection of water vapor on a planet so close in cosmic terms feels both magical and sobering. Magical because it means that water-rich environments might not be rare or isolated. Sobering because vapor alone cannot answer the deepest questions. Does this world breathe through storms? Does it cycle water between its surface and sky? Does it hide oceans beneath its clouds? Or deserts of steam? Does it cradle chemistry that leans toward life? The more scientists examine the water signal, the more they feel the weight of those questions. Water is a prelude, not a conclusion. It is a clue that opens 20 more mysteries. It is a whisper that says, "Look again. There is more here. Keep searching." And that whisper is enough. Enough to ignite new research, new proposals, new missions. Enough to pull humanity's gaze deeper into our local cosmic waters. Enough to make this planet not just another discovery but a symbol. A reminder that the universe is not static, empty, or indifferent. It is active, evolving, and filled with chemistry that echoes our own. In the presence of water, a planet becomes more than a rock or a ball of gas. It becomes a candidate for story, change, and possibility. It becomes a world worth watching, a world worth knowing, a world that might one day help us answer the most profound question we've ever asked. Are we alone? Or are we surrounded by countless worlds where water shapes life as gracefully as it shaped our own? The star at the center of this system is not the kind of blazing celestial titan we imagine when we think of suns. It is small, dim, and deceptively quiet. A red dwarf barely half the size of our sun, glowing with a soft ember-like radiance instead of a blinding blaze. Yet despite its muted appearance, it is ancient and powerful, shaped by billions of years of fusion, magnetic storms, and cosmic endurance. In its faint light, the exoplanet orbits closely, almost intimately, locked in a gravitational embrace that dictates every aspect of the world's climate, atmosphere, and evolution. This star is both a giver and taker, a source of warmth and a source of danger, a cosmic paradox that shapes the planet's past, present, and future. Red dwarfs are masters of longevity. While massive stars burn violently and die young, red dwarfs burn with a slow, steady patience that can outlast almost every other type of star in the galaxy. They can live for trillions of years, far longer than the universe has existed so far. Their energy output is low but persistent, a gentle glow rather than a furnace roar. This means that planets orbiting close enough to be warmed receive a constant, stable stream of light, if they can endure the star's temper. For while red dwarfs shine faintly, they are notorious for sudden bursts of violent activity. Magnetic storms can erupt without warning, releasing flares that surge outward like cosmic tsunamis. Ultraviolet and X-ray radiation can spike in an instant, slamming into any nearby planets like invisible shockwaves. For the exoplanet in question, this relationship is critical. It orbits near enough to its star to receive warmth, perhaps enough for water to exist in vapor or even liquid form. But this proximity brings risk. The planet may be close enough that its atmosphere is constantly sculpted, reshaped, eroded, replenished by the star's energy output. Stellar winds could strip gases from its upper layers, thinning them over millions of years. Flares could ignite chemical reactions, building complex molecules or destroying them in a single surge. This interplay creates a dynamic environment where atmospheric chemistry is a living process, driven not just by the planet itself but by the star that feeds it. The star's light carries more than heat. Its spectral fingerprint imbues the planet's skies with a particular color and flavor. Standing on the planet's day side, if any solid ground exists, one might see a reddish horizon, dim but steady, as though lit by an eternal sunset. The atmosphere could refract the star's light into deep copper tones, or tint clouds with hues never seen on Earth. Winds might circulate heat from the illuminated side to the eternal night beyond, creating violent atmospheric currents that churn across the surface. This dance between light and shadow becomes the heartbeat of the world, driven entirely by the star's faint but relentless glow. Yet the star is not merely a source of warmth, it is a sculptor of chemistry. Its radiation interacts with the planet's atmosphere, breaking molecules apart and encouraging them to recombine into new forms. This photochemistry can produce haze layers, organic compounds, or exotic molecules that might otherwise never arise. It can strip water vapor into hydrogen and oxygen, allowing hydrogen to bleed into space and oxygen to accumulate. In extreme cases, it can sterilize a world long before life has a chance to emerge. But in more moderate conditions, these chemical reactions can lay the groundwork for biology, creating the molecular scaffolding from which life might eventually take shape. The star's age adds another layer of intrigue. If it is older than our sun, then its planets have had far more time to evolve. Billions of years of stellar stability, punctuated by bursts of volatility, create an environment where climates might shift, oceans might form and evaporate, atmospheres might thicken or thin. Such long spans of time open the door to possibilities, geological cycles, biosignature chemistry, or entirely alien environmental processes that evolve slowly across eons. But one question looms larger than any other. Is the planet thriving under its star's gentle glow, or barely surviving its unpredictable storms? Some models suggest that thick atmospheres can withstand even intense flare activity, buffering the surface from radiation. Others propose that magnetic fields could shield the planet, preserving a stable environment in the face of stellar aggression. And there is always the possibility that the twilight region, the Terminator line, acts as a sanctuary, shielded from the worst of the heat and the worst of the cold, allowing chemistry to play out in delicate balance. Still, there is a haunting alternative. the star could be a destroyer as much as a provider. If its flares are too strong, if its winds too fierce, the planet's atmosphere may be constantly stripped and rebuilt in cycles of destruction and renewal. Water vapor might persist only because it is continually replenished from subsurface reservoirs or icy layers. Clouds might form not from thriving oceans but from volatile chemical processes sparked by radiation. Under this scenario, the star becomes a force of instability, keeping the planet in a perpetual state of flux, neither fully habitable nor definitively barren. In this way, the star becomes a character in the story just as compelling as the planet itself. It is the planet's heartbeat, its sculptor, its adversary, and its lifeline. It generates the light that reveals the planet to our telescopes, the radiation that shapes its chemistry, and the energy that keeps its atmosphere alive. Without the star, the planet would be a frozen, silent husk. With the star, it becomes a dynamic world, perhaps temperate, perhaps volatile, perhaps on the knife's edge between survival and annihilation. And as scientists examine the data, they cannot escape the feeling that this star, quiet, dim, unremarkable to the casual observer, is hiding something profound. Within its faint glow lies the secret to the planet's identity. Within its storms lies the key to the planet's atmosphere. Within its ancient light lies the story of a world that might be more alive than we dare to imagine. The star that feeds may nourish or it may scorch, but it is the center of the mystery, and its quiet red glow reaches across 26 light-years, illuminating not only a distant world, but also the tantalizing possibility that life's essential ingredients may be far more widespread than we once believed. Life is a fragile concept, yet an unyielding force, one that emerges wherever conditions allow chemistry to organize itself into something persistent, responsive, and evolving. When scientists look at the newly observed exoplanet and ask whether it could be alive, they are not imagining forests or oceans or complex organisms waving beneath alien skies. They are imagining something far more subtle: patterns, processes, and chemical whispers that suggest the presence of biology. The question is enormous, profound, terrifying, and thrilling all at once. Could this small world, orbiting a quiet red dwarf just 26 light-years away, support life in any form? The answer lies not in photographs, but in chemistry, physics, and the delicate dance between a planet and its star. The first clue comes from temperature. The planet orbits in what might be called a borderline habitable region. Not too hot, not too cold, but teetering on the edge of both depending on atmospheric thickness and heat circulation. Tidal locking, if present, creates an extreme contrast between the planet's blistering day side and its frozen night side. Yet that very contrast could produce winds strong enough to distribute heat across the terminator zone. In this twilight ring, temperatures might stabilize to levels where water can remain vapor or even condense into liquid. For life as we understand it, this zone becomes a cradle, a thin ribbon of possibility carved between fire and ice. Then comes the question of atmosphere. Without a substantial atmosphere, life as we know it cannot exist. JWST's spectral data suggests that the planet does possess a detectable layer of gases, enough to imprint a signature onto starlight passing through it. But the thickness, composition, and stability of this atmosphere remain unknown. Is it thick and insulating like Venus? Thin and fragile like Mars? Filled with steam? Cloaked in haze? The presence of water vapor implies that the planet has some mechanism to trap and circulate heat, but it does not reveal whether the air can protect life from the star's radiation or maintain long-term stability. Some atmospheres act as shields, others act as sieves. And until more data arrives, this world sits in a scientific limbo, its sky potentially life-supporting, yet possibly hostile. Next, scientists consider chemistry. Life needs more than water. It needs carbon or an equivalent element capable of forming complex molecules. It needs energy gradients, reactive compounds, and time. JWST has not yet detected carbon-based molecules on this world. No methane, no carbon dioxide, no organics. But the absence of detection is not proof of absence. Clouds could conceal underlying chemical layers. Weak signals could remain drowned out by noise. Or life, if present, might rely on unfamiliar biochemistry altogether. On Earth, early life adapted to extreme radiation, volcanic heat, deep ocean vents, and frigid polar conditions. If a similar process exists on this distant world, it could thrive in niches we can barely imagine, chemical pockets maintained across the planet's transition from day to night. Magnetic fields also play a crucial role. On Earth, the geomagnetic field shields life from the sun's harshest radiation. On a planet orbiting a flare-prone red dwarf, such protection may be even more necessary. If this exoplanet possesses a molten core that generates a magnetic field, it could maintain atmospheric stability for billions of years, giving life time to evolve. But tidal locking sometimes slows rotation so drastically that magnetic fields weaken or vanish entirely. Without this invisible shield, radiation could strip away the atmosphere molecule by molecule, drying the planet into a sterile husk. Yet there are scenarios, rare but possible, where even a tidally locked world retains its field through internal heat, tidal flexing, or unusual core composition. The interplay of these factors, temperature, atmosphere, chemistry, magnetic shielding, creates a simmering scientific tension. Models suggest multiple futures: a world with warm oceans and gentle clouds, or a world of steaming skies over rocky deserts, or a world where water vapor rises only from melting ice on the day side before refreezing on the night side. Each scenario could support life, challenge life, or completely extinguish the possibility. And with only a handful of transits so far, JWST has provided only a fragment of the full picture. Yet the strongest clue in favor of potential habitability is the planet's age relative to its star. If the star is ancient, then the planet has had billions of years to evolve chemically. Even if it endured violent flare periods in its youth, the atmosphere might have stabilized afterward, creating windows of opportunity for biology to arise. Long spans of time are essential. Life does not appear instantly, it slowly organizes itself across eons. A world with durability, even amid adversity, becomes a world where life can experiment, adapt, and persist. The philosophical weight of this possibility is immense. To imagine life emerging on a world with perpetual day on one side and eternal night on the other is to envision a biology unlike anything on Earth. Perhaps life exists along the terminator zone, feeding on gradients of heat, light, or chemical energy. Perhaps it hides underground, shielded from radiation, flourishing near volcanic vents. Perhaps it drifts as microscopic organisms in thick atmospheric bands, living in clouds like Earth's airborne microbes. Or perhaps the planet is lifeless, but perched on the threshold, holding the right ingredients, waiting for chemistry to take the next step. Scientists do not yet know which reality is true, but what keeps them returning to the data again and again is the growing sense that this planet is not simple. It is not empty. It is not static. It is a world with heat flow, atmospheric motion, water vapor, and a star that both nurtures and threatens it. These are not conditions of a dead world. These are the conditions of a world capable of life. No one can say with certainty whether the planet is alive, but the mystery grows deeper with every spectral observation. Something in the data resists easy explanation, an unresolved anomaly, a subtle deviation in expected patterns. It may be an instrumental quirk. It may be clouds. Or it may be the first hint of a complex atmospheric chemistry influenced by processes we do not yet understand. And so, scientists lean in, breath held, eyes fixed on the spectral lines. They are caught between hope and skepticism, wonder and restraint. Because if this world is alive, if even the simplest microbial biosignature exists there, then the universe is not silent. It is not empty. It is not unique to us. It is alive in more places than we ever dared to dream. And on that distant planet, orbiting its small red star, the possibility of life lingers like a quiet pulse, steady, hidden, waiting to be found. Doubt is not the enemy of discovery. It is the force that keeps discovery honest. In the world of exoplanet science, every breakthrough carries a shadow of uncertainty. The detection of water vapor on a distant world is thrilling, almost intoxicating, but it demands caution. Nature has a way of disguising its truths behind misleading signals, and telescopes, no matter how advanced, can sometimes be fooled. Scientists know this well, which is why the moment excitement rises, skepticism rises alongside it. Before anyone can claim that the planet truly holds water, they must confront the possibility of false positives. Signals that mimic something extraordinary but turn out to be ordinary after all. False positives take many forms. Some are born from instrument quirks, tiny fluctuations in sensor readings, faint distortions in the telescope's optics, or calibration errors so subtle that they leave fingerprints indistinguishable from real atmospheric features. JWST is more precise than any telescope before it, but even its perfection must be examined with scrutiny. When the water signature appeared, researchers immediately wondered, could the feature be a result of detector noise? A thermal shift in the telescope's own components? A mathematical artifact introduced by the processing pipeline? These questions are not signs of doubt. They are signs of discipline. Then there are the astrophysical imposters. A planet orbiting a red dwarf experiences stellar flares, surface spots, and magnetic distortions that can all influence the starlight passing through its atmosphere. A cool starspot rotating across the star's surface can mimic a dip in certain wavelengths, producing patterns that resemble molecular signatures. A sudden flare can inject energy that alters the spectrum in unpredictable ways, creating illusions that masquerade as atmospheric molecules. Researchers must disentangle all of these factors before believing what the spectrum appears to say. Clouds add another layer of complication. Thick, high-altitude clouds, whether composed of water droplets, methane ice, sulfur compounds, or exotic chemicals, can flatten and distort spectral signatures. A cloudy world might appear to show water vapor even if only a thin, upper layer contains moisture, while the deeper atmosphere is dry and hostile. Conversely, clouds might mask real molecules beneath their reflective haze, making a world seem chemically barren when it is anything but. Clouds are notorious for playing tricks on observers, and on a planet orbiting a volatile red dwarf, cloud formation may follow patterns unlike anything seen on Earth. Chemistry itself can deceive. Some molecules produce absorption features that overlap with water's spectral lines. Carbon monoxide, methane, and certain hydrogen-rich mixtures can mimic the subtle curves associated with water vapor. Photochemical reactions triggered by stellar radiation may create temporary molecules that absorb light in nearly identical ways. In such cases, a false positive emerges not through error, but through cosmic coincidence. The universe, with all its complexity, sometimes arranges molecules in ways that confuse even the sharpest instruments. There is also the danger of interpretive bias. Humans are storytellers by nature, and when a signal hints at something as profound as water on a nearby exoplanet, the imagination races ahead of the evidence. Scientists must actively resist the urge to see what they hope to find. They must step back, challenge their assumptions, and explore every mundane explanation before considering an extraordinary one. This process is painstaking, slow, and often frustrating. But without it, discoveries lose their integrity. As the team studied the spectral data, they encountered inconsistencies, tiny deviations that refused to fit cleanly into the model of a stable, water-rich atmosphere. Some wavelengths showed deeper absorption than predicted. Others showed flattening where peaks should have appeared. These anomalies could be hints of complex atmospheric chemistry, or they could be noise. The challenge is to determine which conclusion is real without knowing anything about the planet firsthand. Additional transit observations are needed to confirm the water signature, but scheduling them requires months of waiting, precise timing, and meticulous coordination. During that time, alternative theories emerge. Could the planet be surrounded by a ring of vaporizing material left behind by a moon or fragment? Could escaping hydrogen from the upper atmosphere interact with oxygen in such a way that produces a misleading signal? Could we be observing the aftermath of a recent atmospheric loss event? A planet shedding vapor like steam from a boiling pot? These questions are not obstacles to discovery. They are the scaffolding that ensures discoveries withstand the test of time. Every hypothesis must be challenged. Every anomaly must be explained. Every possibility must be explored, no matter how unlikely. Because the universe does not hand us its secrets willingly. It reveals them slowly, carefully, often wrapped in layers of misdirection. Yet the very presence of these doubts does something remarkable. It deepens the mystery. If the water signal is real, it changes our understanding of nearby worlds. If it is false, then what created it? If it is incomplete, then what complexities are hiding beneath the surface? Even skepticism becomes a kind of wonder, because every potential explanation opens a new avenue of inquiry. The shadow of false positives hangs over every claim in exoplanet science, but it does not diminish the excitement. Instead, it sharpens it. It forces scientists to push harder, think deeper, question more boldly. And as they weigh each interpretation, hope against caution, possibility against restraint, the planet remains suspended in uncertainty, its true nature obscured by both clouds and doubt. But uncertainty is not a dead end. It is the beginning of deeper exploration. Because if the signal is real, the world is extraordinary. And if the signal is false, the universe has played a clever trick. One that may lead us toward discoveries just as profound. The deeper scientists studied the anomaly's emissions, the more they began to notice something strange, something rhythmic, something almost alive. Amid the cold silence of deep space, the object released pulses of energy that did not behave like ordinary radiation. They weren't random bursts, nor were they the predictable oscillations of a rotating star. Instead, they formed a pattern so delicate, so consistent, that it resembled a heartbeat echoing across the void. It was a slow, ancient pulse, steady enough to measure, gentle enough to miss if you were not looking for it, yet profound enough to alter everything researchers believed about the origins of cosmic structure. The pulse wasn't like the rhythmic flashes of a pulsar or the chaotic thrum of a black hole's accretion disk. It moved with eerie smoothness, cycling through frequencies that remained stable over multiple observations. Each pulse radiated through the infrared spectrum with a soft rise and fall, as though the object were inhaling and exhaling energy. This stability was impossible for something so ancient. Natural cosmic rhythms decay, drift, deform. Yet this pulse persisted with the grace of a metronome older than spacetime. Scientists began calling it the ancient pulse, a name that carried equal parts wonder and fear. Spectral analysis revealed something even more unsettling. The pulses were not uniform. They carried shifts in energy intensity that resembled encoded information, not intentional communication, but the kind of structure that emerges when a physical system oscillates between states. In the early universe, no matter could have such stability. No cosmic environment was calm enough to support it. Yet the anomaly produced a pattern that seemed to originate from an environment far older and far more stable than the post-Big Bang cosmos. It was as though the object had preserved the conditions of its birth and continued to echo them across billions of years. The pulses also interacted strangely with surrounding space. Normally, energy radiates outward in a smooth wave, but these pulses distorted spacetime subtly, creating ripples that extended far beyond the object's visible boundary. They bent the trajectories of photons in ways that did not match gravitational theory. It was as if the object were momentarily altering the shape of reality with each rhythmic emission. The ripples resembled predictions from theories involving early universe scalar fields, fields that might have existed before gravity took its modern form. Each pulse felt like the faint memory of a universe governed by rules no longer active. When scientists graphed the pulse frequencies, they discovered something beautiful and terrifying. The rhythm followed a mathematical sequence that appeared across multiple scales, harmonics that suggested order, symmetry, and ancient cosmic balance. These harmonics resembled those seen in simulations of quantum fields transitioning from chaos into structure. It was as if the object still carried the echo of the moment when the universe first cooled from quantum noise into spacetime geometry. The anomaly's pulse became a living fossil of that transition, a fragment of history vibrating in real time. Some physicists proposed that the pulse originated from internal conflicts between incompatible phases of matter inside the object. As ancient material tried to stabilize within the constraints of our universe's physical laws, it might oscillate, producing periodic energy bursts. Others believed the pulse might be the residue of pre-Big Bang cosmic cycles, a kind of temporal inertia left over from a previous universe's collapse. In this interpretation, the pulse was not merely a physical phenomenon but a temporal echo, a leftover rhythm from an earlier universe beating faintly inside the current one. A more radical group suggested that the object might be a remnant of a cosmic structure that behaved like a universe-scale clock, regulating the unfolding of pre-Big Bang physics. If such structures existed before spacetime solidified, they might have imprinted their internal rhythms on whatever survived the transition. The anomaly, then, could be one of the last active clocks from a forgotten era, still ticking with a beat older than time. What made the pulse truly chilling, however, was its effect on nearby void regions. Instruments detected faint synchronization patterns in the vacuum surrounding the anomaly, as if empty space were resonating with the object's rhythm. This phenomenon resembled quantum coherence on a massive scale, suggesting that the object was influencing the vacuum state itself. If true, it meant the anomaly was not just broadcasting energy, it was harmonizing the structure of space around it. It was changing the vacuum, restoring a pattern that may have existed before the Big Bang. This discovery produced an unsettling philosophical shift. If the universe has a pulse, if ancient rhythms still echo beneath spacetime, then perhaps everything we observe today is built upon deeper patterns born long before galaxies formed. Perhaps consciousness, matter, energy, even time itself trace their roots to those primordial rhythms. The anomaly's pulse became more than a scientific curiosity. It became a reminder that the cosmos may be alive in ways we never expected, driven by cycles older than any star, any law, any universe. Emotionally, the pulse affected everyone who studied it. Hearing its reconstructed sound, converted from infrared oscillations into audible frequency, felt like listening to the heartbeat of reality itself. Slow, deep, ageless. It stirred something instinctual, something ancient in the human mind. The pulse was not simply a signal, it was a presence. A quiet, timeless presence that resonated beyond logic and raised unsettling questions. Was this the rhythm of a previous universe? A leftover beat from cosmic creation? Or the final echo of something that once existed in the darkness before existence? Whatever its origin, the pulse remained constant, unwavering, as if refusing to let its ancient story fade. It suggested that the universe carries memories deeper than the Big Bang, that beneath the surface of spacetime, faint echoes of forgotten epochs still linger, silently shaping the cosmos. The ancient pulse continued, steady and unbroken, whispering across the void like the last heartbeat of a world that came before ours. There is a strange and familiar ache that comes from seeing parts of our own world reflected in a distant one. When scientists analyze the spectrum of this exoplanet, they find themselves drifting into a kind of cosmic déjà vu, a sense that they have glimpsed something like this before, not in the cold vacuum of space, but in the ancient history of Earth. Long before continents formed, before oxygen filled the skies, before even the simplest cells learned to divide, Earth was a raw and unstable world. Its oceans simmered with volcanic heat. Its atmosphere thickened with vapor and chemicals that danced in cycles we can only imagine. To compare a distant planet to that early Earth is not to claim they are identical. It is to recognize echoes, resonances, and hints of familiar chemical rhythms in an alien environment. Imagine Earth 4 billion years ago. The sky was not blue but tinted with haze, orange, red, sometimes greenish, depending on what volcanic gases filled the air. Lightning storms crackled across an oceanic surface that spanned nearly the entire globe. Hydrothermal vents on the ocean floor spewed minerals into warm, mineral-rich water. Clouds formed, collapsed, and reformed in endless cycles. Rain fell in steaming sheets. Sunlight struggled through thick atmospheres, warming and cooling the planet in erratic pulses. Life, if it existed at all, survived in microscopic, fragile forms, clinging to vents, floating in shallow pools, or hiding beneath layers of sediment. It was a world both hostile and full of potential. Now imagine the exoplanet. Small, close to its star, perhaps with vapor swirling in its skies. The red dwarf that warms it provides a softer, dimmer light than the early sun once did, but that light is steady and persistent. If the planet possesses water vapor, if it truly has moisture cycling through its air, then it may be experiencing something similar to Earth's early hydrological cycles. Water rising as vapor on the day side, drifting into the twilight zone, condensing on the cold night side. Slow, patient flows of energy shaping the atmosphere. Temperature gradients creating winds that carve patterns through the sky. These processes might not look like Earth's, but the underlying physics remains universal. In some models, the planet resembles early Earth in atmospheric composition. Water vapor dominates, mixed with hydrogen or carbon-rich gases. This combination creates layers of haze, similar to the organic aerosols that once filled our planet's ancient atmosphere. Such haze can alter climate, trap heat, scatter light, or even provide protection from stellar radiation. On Earth, haze played a role in shielding early life from ultraviolet storms. On this distant world, haze could be performing the same function, protecting molecules forming in the planet's thin or thick atmospheric boundaries. Scientists find this parallel tantalizing. Early Earth was not a world that looked promising from afar. Its surface was chaotic, its atmosphere unstable, its climates violently unpredictable. And yet, within that chaos, life found a foothold and slowly grew. If this exoplanet shows atmospheric features similar to early Earth, mist-filled air, vapor cycles, high clouds, temperature transitions, it becomes a kind of cosmic mirror, reflecting the possibility that life might emerge not in comfortable conditions, but in challenging ones. There are deeper similarities as well. Early Earth was shaped by internal heat. Volcanic plumes belched steam and minerals into the environment. Geothermal energy provided chemical gradients, differences in temperature and composition that early organisms could exploit. If this exoplanet is tectonically active, if it possesses volcanic vents or internal heating driven by tidal stresses, it might also produce rich chemical gradients. These gradients are essential for the emergence of life. They represent energy sources that can drive complex, self-sustaining reactions. Life on Earth began not in gentle sunshine, but in violent, mineral-rich, heat-driven environments. The exoplanet's close orbit raises another possibility. Tidal locking could create a narrow habitable zone along the Terminator line. While Earth has global oceans, global climates, and global weather systems, this world might have linear ones. Imagine a ring around the planet where perpetual twilight reigns. This line, neither too bright nor too dark, could host stable temperatures ideal for liquid water. Winds would sweep constantly through this region, carrying moisture from one hemisphere to another. Along this twilight belt, clouds might gather in persistent arcs, condensing into rain or snow that drifts into darkness. To imagine life on such a world is to imagine biology not constrained to a globe, but to a ring, a narrow, circular continent of perpetual dawn. This idea fascinates scientists. It suggests environments unlike Earth's, yet built from the same ingredients. On early Earth, life adapted to extreme conditions. Boiling vents, acidic waters, icy environments, ultraviolet bombardment. On the exoplanet, life, if it exists, would face its own extremes. Temperature differentials, atmospheric variations, stellar flares. Yet life, by its nature, does not seek comfort. It seeks survival. And survival often emerges in the strangest circumstances. Even the water vapor signature evokes early Earth. Billions of years ago, Earth's atmosphere was rich in steam. Massive volcanic eruptions released oceans' worth of vapor. As the planet cooled, this vapor condensed into the first true seas. If the exoplanet is undergoing a similar phase, if it is a world transitioning between vapor and liquid cycles, it might resemble Earth during the era when life began to take shape. The presence of water vapor is more than a chemical clue. It is a temporal clue. It suggests the planet could be at a stage of evolution that parallels a critical chapter in Earth's own story. But these comparisons also fuel a haunting contradiction. If the exoplanet is too similar to early Earth, then it may still be hostile to life. Lightning storms, high radiation, unstable climates. These could render the planet uninhabitable, at least for complex organisms. Early Earth was not gentle, and neither might this world be. Yet even that does not rule out the possibility of microbial life. Microbes are resilient. They can thrive in acidic lakes, freezing deserts, boiling vents, radiation-soaked soils. If life has arisen anywhere else, it may well have arisen in conditions like these. The scientists studying this exoplanet understand that these parallels do not prove anything. They do not claim that the planet is Earth's twin or that life exists there. What they see instead are patterns. Patterns that make them pause, reflect, and imagine. Patterns that invite them to think not about what life is, but about what life could be. Patterns that whisper across light years, reminding them that the boundary between Earth's ancient past and a distant world's present may be thinner than they once believed. When worlds echo Earth, they force us to reconsider our uniqueness. They challenge the notion that life emerged through a cosmic accident. They imply that under the right conditions, water, heat, chemistry, time, life might be an expected outcome rather than an anomaly. And they remind us that Earth, for all its beauty, may not be the only world shaped by water, warmed by a star, and touched by the quiet spark of biology. On this distant planet, orbiting a dim red sun, the echoes grow stronger. They do not confirm life, but they do something almost as powerful. They suggest that the universe might be filled with worlds bearing familiar stories, unfolding in unfamiliar ways. And somewhere beneath the haze and vapor, the planet continues its slow, ancient evolution, perhaps mirroring the steps our own world once took, long before we learned to look for ourselves in the stars. Proximity carries a strange kind of gravity, not the physical pull of mass, but the emotional pull of possibility. When scientists realized that the planet showing hints of water vapor was only 26 light-years away, the discovery took on a new weight. This wasn't a distant galaxy billions of years removed from us. It wasn't a world so far across the cosmos that its light began its journey before Earth existed. This was a neighbor close enough that, in cosmic terms, it sits just down the interstellar street. And with that closeness comes a profound shift in perspective, one that merges science with philosophy, logic with awe. 26 light-years is unimaginably far for human travel today, but staggeringly close when we consider the size of the Milky Way. Our galaxy spans 100,000 light-years. This planet lies within a botanical garden's distance compared to that scale. The idea that a potentially water-rich world exists within that radius reframes our understanding of cosmic rarity. For decades, scientists assumed planets capable of supporting the ingredients for life were sparse, perhaps scattered thinly across the galaxy like rare gemstones. But now, with telescopes like JWST revealing so many nearby candidates, that assumption is dissolving. If one such world exists this close, how many more might be hiding within the next few dozen stars? This thought provokes both hope and unease. Hope because proximity means feasibility, feasibility for future exploration, for robotic missions centuries from now, for interstellar mapping that goes beyond imagination. Unease because the presence of such worlds so near to us deepens the question of cosmic silence. If the universe is filled with planets on the threshold of habitability, why does the night sky feel so quiet? Why don't we see signs of civilizations, signals, megastructures, disturbances in starlight that indicate technological activity? The closer, potentially habitable worlds are, the louder this philosophical question becomes. But proximity also makes the discovery personal. It forces us to imagine this planet not as a distant abstraction but as a real place, orbiting a real star, moving through real seasons and weather cycles. Picture it. A tiny globe circling its red dwarf, with vapor drifting through its skies, clouds forming over a twilight belt, and temperature gradients sculpting patterns across its surface. A world like that feels less like a concept and more like a location, a destination, even if humanity may never set foot there. It becomes part of our extended neighborhood, a world we may someday map, model, and know as intimately as we know Mars or Venus. There is something deeply philosophical about the idea of nearby worlds. It challenges our place in the universe. For thousands of years, humanity believed Earth was the center of creation. Then we learned the sun was just another star, and our solar system just another system. Now, we are learning that even the stars nearest to us might harbor planets with water, chemistry, and complex atmospheres. This realization shatters any lingering illusions of cosmic centrality. We are not isolated. We are not unique. We are part of a vast, interconnected web of worlds orbiting billions of stars. And yet, the proximity of such worlds also magnifies our vulnerability. If planets with water exist only dozens of light-years away, then life, simple or complex, could emerge just as easily elsewhere. Life, in that sense, becomes a universal process, not a rare and improbable phenomenon. But that also means civilizations, if they arise, might be just as fragile as we are. They might live and die in the blink of cosmic time, their existence lost before their signals ever reach another world. Proximity does not guarantee communication. It merely increases the possibility while deepening the mystery. For scientists, the philosophical implications of closeness fuel debates that stretch late into the night. If this planet is so near to us, what does that imply about how planets form? About how common water-rich environments are? About how life might spread through the galaxy? Some whisper theories of panspermia, life traveling on interstellar debris. Others question whether life emerges independently everywhere conditions are right. Still others speculate about quiet biospheres, worlds with microbial life that never evolves intelligence, existing indefinitely in silent stability. But proximity also stirs a sense of responsibility. If such worlds exist nearby, then humanity carries an ethical burden. What happens when we develop telescopes powerful enough to see the surfaces of neighboring planets? What happens when we detect biosignatures or worse, technosignatures? How do we react? With caution? With awe? With fear? With curiosity? The future of astronomy becomes entangled with the future of humanity's moral compass. Then there is the question that sits at the heart of every debate, quiet but relentless. If we find a world so close to us with water, chemistry, and potential habitability, then why haven't we found signs of life yet? Is life rare, or is communication rare? Is intelligence unusual, or is survival unusual? In the silence, proximity deepens the paradox. Because a world 26 light-years away is not beyond reach, not beyond detection, not beyond understanding. If life were there, shouldn't we have seen something by now? And yet, we haven't. The universe remains silent. That silence is not empty, though. It is charged with possibility, with questions, with emotion. It makes the discovery feel heavier, more intimate, more urgent. A world so near forces humanity to confront not only the universe, but itself. Our assumptions, our fears, our hopes, our loneliness. The philosophy of proximity is simple and profound. The closer the mystery stands, the more it reflects who we are. This nearby planet, draped in vapor and illuminated by the glow of its small red star, becomes more than an object of study. It becomes a mirror, one that reflects our longing for connection, our hunger for understanding, and our quiet suspicion that the universe may be far more alive than the silence suggests. Cosmic silence is one of the most unsettling truths we've ever encountered. It hangs over every discovery, every observation, every breathless announcement. We are surrounded by billions of stars, trillions of planets, and countless galaxies stitched across an immeasurable universe. Yet not a single confirmed signal, structure, or whisper of intelligent life has reached us. This contradiction lies at the heart of the Fermi paradox. The universe appears rich with potential for life, yet remains oppressively, mysteriously quiet. And now, with a nearby exoplanet showing hints of water vapor, a key ingredient for habitability, the paradox becomes even sharper, more personal. If life-friendly conditions exist so close to us, why does the cosmos feel so empty? The discovery of water vapor on a world only 26 light-years away intensifies this contradiction like a tightening coil. This isn't a far-flung galaxy billions of light-years out, where life might exist today but be forever separated from us by time. This is a world practically next door on the cosmic scale. If planets like this are common, if water and atmospheric complexity are standard features of nearby systems, then the universe should be overflowing with life. Over billions of years, even slow-moving technological civilizations could have spread signals, probes, or visible megastructures across the galaxy. We should see something by now, some hint, some anomaly, some undeniable trace. Instead, we see nothing. The silence hangs like a velvet curtain over the night sky, soft but impenetrable. It's a quiet that feels unnatural, as if something is missing. Scientists cannot ignore this tension. Every time a potentially habitable planet appears in the data, every time JWST uncovers another atmospheric signature that mirrors Earth's early chemistry, the paradox grows louder. If the conditions for life are common, then intelligent life should be old, widespread, and technologically advanced. So where is everyone? There are many answers, and all of them are unsettling. Perhaps civilizations are fragile. Perhaps life arises often, but intelligence rarely persists. On Earth, countless species lived and died before humans emerged, and even now our civilization feels precarious, one miscalculated catastrophe away from collapse. If intelligence is a flame that rarely burns long enough to be seen across space, then silence becomes expected. The universe might not be empty. It may simply be filled with civilizations that flicker briefly and disappear before their voices travel far. Or perhaps life evolves frequently, but intelligence is an evolutionary accident, a rare convergence of traits, pressures, and circumstances. Earth's history shows that for billions of years, life thrived without developing advanced cognition. Microbes, plants, fungi, simple animals, they dominated the planet long before humans appeared. If intelligence is not inevitable, then most habitable planets might be alive but quiet, their biospheres flourishing without ever developing the ability to communicate. Another possibility is that civilizations choose silence. Perhaps they observe from afar, quietly, without announcing their presence. Or perhaps communication is seen as a risk, a beacon inviting danger. Maybe advanced beings hide their signals under the cosmic noise, avoiding attention in a universe where survival demands secrecy. Silence, in this interpretation, becomes a strategy, not an accident. But the most terrifying explanation is that silence may be enforced. Some theorists imagine a cosmic filter, a barrier that prevents civilizations from advancing to the stage where they can travel or communicate widely. This filter could lie behind us. Life is rare, intelligence is freakish. Or it could lie ahead of us. Civilizations destroy themselves before they can become spacefaring. If the great filter lies ahead, then humanity stands on the edge of a precipice without realizing it. And a nearby habitable world becomes not a comfort, but a warning. Conditions for life are easy. Surviving long enough to be heard is not. The exoplanet with water vapor becomes a symbol of this paradox. It is close enough that, if life were thriving there, its chemical footprint might eventually reach our instruments. If an intelligent civilization flourished on such a world millions of years ago, its signals could already be crossing the void. If it built structures large enough to affect the star's light, JWST might detect them. But the data shows no such anomalies, no artificial spectral features, no unnatural patterns, no signs of engineered emissions. Just water, just clouds, just a world that feels alive, but not alive in a way that speaks. This deepens the emotional tension for scientists. The closer we get to identifying habitable worlds, the more oppressive the silence feels. It's as if the universe is deliberately holding its breath. We find planets capable of supporting oceans, yet no evidence of oceans filled with life. We find planets with atmospheres, yet no trace of atmospheric chemicals associated with biology. We find planets in the habitable zone, yet no hint of civilization. The universe is like an empty stage richly decorated for a play no one ever performs. But silence is not always a verdict. Sometimes silence is a frontier. Perhaps the universe has only just begun producing civilizations capable of reaching across the stars. Perhaps we are among the first or the very first to develop technology sensitive enough to detect life elsewhere. In that case, the silence is temporary, a calm before a storm of discoveries. Or perhaps we are simply listening wrong, using the wrong frequencies, the wrong assumptions, the wrong methods. Our search is still primitive, still narrow, still based on what we would do, not what alien intelligence might do. The universe may be filled with communication styles we haven't even imagined: quantum signals, neutrino beams, gravitational pulse patterns, or biochemical emissions detectable only to species evolved under conditions nothing like Earth's. Yet the paradox remains. And as scientists weigh every explanation, the exoplanet becomes more than a distant world. It becomes a philosophical puzzle. A reminder that life might be common, intelligence might be rare, and communication might be nearly impossible. The silence becomes a character of its own. Not emptiness, but a presence, a question mark carved into the fabric of the universe. A reminder that the cosmos, for all its beauty and complexity, still guards its secrets. And lurking within that silence is the possibility that the quiet itself is a kind of message, a warning, a boundary, or an invitation to listen more closely. Because if we ever break that silence, if we ever hear a signal from another world, everything we understand about ourselves, our future, and our place in the cosmos will change forever. Until then, the universe remains both hauntingly silent and overwhelmingly full of promise. Preparing for a new observation of a distant world is nothing like pointing a telescope and waiting. It is a slow, meticulous, almost ritualistic process, one that blends engineering precision with the high-stakes tension of scientific exploration. For a planet showing hints of water vapor, every upcoming observation window becomes a rare and precious opportunity. The world orbits its star in a tight, predictable rhythm, and JWST must align itself perfectly during these moments when the planet passes in front of its star. These transits are brief, fragile openings, cosmic shutters that open only for a few hours, offering a narrow view into an alien atmosphere before snapping shut again for weeks or months. Because of this, scientists strategize like chess masters. They calculate timing down to the second, accounting for the telescope's position, the star's angle, thermal constraints, solar protection, and scheduling conflicts with other high-priority targets. JWST is constantly in demand. Galaxies at the edge of time, black holes shredding stars, nebulae rich with the ingredients of life, and now exoplanets whispering with faint signals of water. The team must argue convincingly that this planet deserves additional precious hours of observation time. And with a signal as tantalizing as water vapor so close to home, they argue fiercely. The preparation begins with data from previous observations. Scientists examine the spectrum, searching for gaps, wavelengths where the signal was too faint or noise too high or features too ambiguous. They identify which infrared bands might reveal more clarity about water absorption, cloud structures, atmospheric thickness, or unknown molecules hiding beneath the noise. The telescope's instruments are then programmed to observe those exact wavelengths during the next transit, maximizing the possibility of extracting new information. Every calibration must be flawless. Every sensor must be tuned. Every second must count. Teams from around the world collaborate, cross-checking calculations, refining atmospheric models, predicting how the planet's orbit might shift due to gravitational interactions or star-spot activity. Even the star's mood matters. Red dwarfs are unpredictable, prone to bursts of radiation. A flare during a transit could ruin hours of data, contaminating the spectrum with noise. To guard against this, scientists monitor the star constantly using ground-based telescopes, satellites, and automated alert systems. When a flare erupts, they take notes, adjust models, and prepare for how the flare might affect the next observation. The tension builds as the observation window approaches. JWST is positioned far from Earth, orbiting around the L2 Lagrange point, where temperatures remain stable and light interference is minimal. Yet even here, the telescope must rotate, tilt, and align with extreme precision. If its sun shield tilts incorrectly by even a fraction of a degree, heat could seep into the instruments and distort the data. Engineers run simulations to ensure the telescope remains oriented safely, while astronomers finalize the list of wavelengths to capture. When the moment arrives, the world below falls silent. In control rooms and research offices, scientists gather behind glowing monitors, eyes fixed on data streams flowing from a telescope a million miles away. They watch as the starlight dims, just slightly, as the planet begins its transit. For a few hours, this distant world becomes the center of human attention. Every photon matters. Every curve in the light curve tells a story. As the atmosphere imprints itself onto the starlight, scientists begin to see faint features emerging. A deeper dip here, a smoother curve there. They cannot yet interpret them, but their hearts race with the knowledge that something new is being captured, something no human has ever seen before. Once the transit ends, the tension shifts to anticipation. The raw data is transmitted slowly, meticulously, checked for corruption along the way. It arrives in segments, each one a fragment of a cosmic puzzle. Teams around the globe receive it, process it, filter out noise, subtract baseline variations, and stitch the segments together into a spectrum. They compare it to previous observations, looking for changes, consistencies, contradictions. And often, those contradictions are the most exciting part. If the water vapor signal appears again, it strengthens the claim that the planet truly possesses atmospheric moisture. If the signal grows stronger or weaker, it may hint at clouds, storms, or atmospheric variability. If entirely new molecular features appear, methane, carbon dioxide, or something unexpected, the discovery instantly becomes revolutionary. Scientists know that each observation window is more than routine. It is a step deeper into the unknown, a narrowing of possibilities, a sharpening of truth. They also know that future windows may bring surprises. A stellar flare contaminating data, a cloudy atmosphere muting signals, or an unexpected atmospheric shift that challenges every existing model. And looming beyond these windows is a broader horizon. Plans for next-generation telescopes, LUVOIR, HabEx, LIFE, and others, are being shaped partly by discoveries like this one. The data from JWST fuels debates about what instruments future missions must carry. Larger mirrors, better coronagraphs, finer spectrometers capable of revealing biosignatures like oxygen, methane, or ammonia. The exoplanet becomes a test case, a proving ground for humanity's future attempts to detect life light years away. As anticipation builds for the next observation, scientists feel something deeper than curiosity, responsibility. This world is close. Its signals are reachable. Its mysteries are solvable within our lifetime. Each new window is not merely an observation opportunity. It is a chance to reshape humanity's understanding of its place in the universe. The next observation window is coming. The telescope is ready. The world waits. And somewhere, 26 light-years away, the planet continues to orbit its small red star, unaware that an entire species is watching its every transit, hoping, questioning, dreaming, preparing for the moment it finally reveals the truth hidden within its thin veil of starlight. The search for exoplanets once relied on blurred hints and distant shadows. Now, with telescopes like JWST rewriting the boundaries of possibility, humanity stands at the dawn of a new era. One where entire worlds are no longer abstractions but intricate, evolving places we can study in exquisite detail. Yet JWST is only the beginning. Its golden mirrors have opened the door, but the future of exoplanet exploration will push that door wide, flooding our understanding with clarity and answers we cannot yet imagine. Section by section, mission by mission, humanity is assembling an arsenal of tools designed not just to detect distant planets, but to know them, to map their atmospheres, analyze their chemistry, read their climates, and even search directly for signs of life. The future begins with precision. Missions currently in development are being designed with sensitivity levels far beyond JWST's capabilities. They will stare at the atmospheres of exoplanets with the same attention JWST gives to galaxies at the edge of time. LUVOIR, the large UV/optical/IR surveyor, is one such mission. Planned with mirrors up to 15 meters across, it could detect oxygen or methane on Earth-sized planets orbiting sun-like stars. LUVOIR would not merely observe the tiny dips in starlight as a planet transits. It could directly image the faint glow of worlds beside their stars, revealing sky colors, weather patterns, and even surface features through layered atmospheric signatures. For the first time, humanity might glimpse blue oceans, swirling cloud patterns, or hazy atmospheres enveloping alien continents. The habEx Observatory, another proposed mission, focuses on the quiet art of isolation, blocking starlight so completely that the planet's own light can be examined without interference. It will use a starshade, a massive, petal-shaped structure flying tens of thousands of kilometers ahead of the telescope. This structure will cast a perfect shadow over the telescope's instrument array, allowing scientists to see planets 1 billion times fainter than their host stars. With such a tool, HabEx could hunt Earth twins, measuring their atmospheres for biosignatures and taking humanity's search for life from speculative to scientific. Europe is preparing its own missions, the Atmospheric Remote Sensing Infrared Exoplanet Large Survey, or ARIEL, which will study the atmospheres of hundreds of exoplanets. While JWST can focus on only a few at a time, ARIEL will conduct large-scale surveys, building a detailed catalog of atmospheric diversity. It will reveal how common water vapor is, how atmospheres evolve across different orbits and temperatures, and how chemistry varies between rocky planets, mini-Neptunes, and gas giants. ARIEL's data will act like a cosmic census, showing humanity the range of planetary environments close to home. Beyond these telescopes, the future moves toward an even more ambitious dream: interferometry, linking multiple telescopes together to create a single, enormous virtual mirror. Concepts like the LIFE mission Large Interferometer for Exoplanets envision fleets of telescopes flying in formation, collecting light with impossible precision. Such systems could resolve details at the scale of continents. They could measure heat signatures from alien surfaces or detect small temperature variations across a planet's atmosphere. Interferometers might even reveal seasonal changes, storms growing and fading, polar ice waxing and waning, heat shifting across hemispheres, all from dozens of light-years away. But the technological evolution does not stop at telescopes. Spectroscopy is becoming more refined, expanding into wavelengths that JWST cannot access. Instruments are being designed to detect molecules associated not just with life, but with industrial activity, like nitrogen dioxide or chlorofluorocarbons. Future missions may attempt to spot megastructures, harvest patterns in starlight, or observe anomalies in planetary brightness indicative of artificial energy use. These explorations redefine how humanity searches for intelligence, not by listening for radio signals alone, but by studying the physics of light for anything that deviates from natural behavior. At the same time, humanity is pushing toward more daring ambitions, sending probes, even slowly, toward nearby stars. Projects like Breakthrough Starshot imagine fleets of ultralight nanocraft propelled by powerful lasers, accelerating to a fraction of the speed of light. Within a few decades, such probes could pass by planets around Alpha Centauri, capturing images and sampling environments directly. If successful, the same strategy could target other systems, including those with water vapor signals, turning distant worlds into reachable frontiers. As technology evolves, so does philosophy. The future of exoplanet exploration challenges humanity to ask deeper questions. What counts as life? Is life defined by carbon and water, or could alien biology arise from entirely different foundations? How do we interpret biosignatures when unfamiliar chemistry could produce similar signals? What if life exists in forms too simple to detect, or too advanced to reveal itself? Each mission forces humanity to refine its understanding of biology, chemistry, and even consciousness. The discoveries ahead will not be quiet. They will spark debates, challenge assumptions, and provoke awe. Scientists will argue over anomalous spectra. Philosophers will question humanity's significance. Engineers will debate the ethics of sending probes. The public will react with wonder or fear. Governments will grapple with the implications of finding worlds that mirror our own. The search for life will become not just a scientific mission, but a cultural one, a turning point in human history. And as new telescopes and missions come online, the planet with water vapor, this quiet world orbiting a dim red star, will remain a touchstone, a training ground, a benchmark, a world that shaped the strategy for future exploration. It will continue to teach us what to look for, how to interpret chemical clues, and how to follow faint signals through cosmic noise. It will remind us that even small planets around small stars can hold tremendous secrets. The future of exoplanet exploration is not one mission, but a rising tide of discovery, a convergence of instruments, ideas, and ambitions. As we refine our tools, the universe refines its mysteries, offering clearer glimpses of worlds that might be alive, might be strange, might be familiar, or might be entirely beyond our imagination. Humanity stands at the edge of that new era. We have begun to see the path forward. And the universe, once silent and unknowable, is finally beginning to speak. If we were to discover life on a distant exoplanet, even the simplest, faintest trace of microbial chemistry, the impact on humanity would be immediate and overwhelming. It would be a revelation that shakes the foundations of science, religion, philosophy, and culture. Not because life elsewhere threatens us, but because it redefines what it means to be alive, what it means to be human, and what it means to be part of a universe far more complex and inhabited than we ever imagined. Section 17 explores that shock, the emotional, intellectual, and existential cascade that would follow the confirmation of life beyond Earth. The first moments would be a tidal wave of disbelief and awe. News anchors would speak with trembling voices. Scientists would struggle to articulate the magnitude. People worldwide would pause mid-meal, mid-work, mid-thought, frozen by the realization that we are not alone. The discovery wouldn't merely add a new chapter to textbooks. It would rewrite the first page. For centuries, humanity has wondered whether life exists elsewhere. The moment that question is answered, yes, definitively yes, the human story changes. But the nature of the shock depends on what kind of life we find. If it is microbial, the revelation is profound yet comforting. Life is not unique. Life is not a miracle confined to Earth. Life emerges wherever physics and chemistry provide the right conditions. Microbes on another planet would suggest that biology might be woven into the fabric of the cosmos, a common outcome, not a cosmic accident. This discovery would ignite hope. If simple life is widespread, then complex life may not be far behind in other systems. Intelligent life, too, might exist in quiet corners of the galaxy. The universe becomes a living tapestry, and Earth becomes a single thread. If the life is more complex, multicellular organisms, ecosystems, structures, or patterns resembling early flora, the impact becomes even more dramatic. Such life would indicate that evolution progresses beyond microbial simplicity on other worlds. Complexity might flourish across the galaxy, shaped not by Earth-like conditions, but by universal principles of adaptation and growth. Philosophers would speak of a living cosmos. Biologists would rewrite evolutionary theory. Thousands of research programs would launch overnight. But if we were to discover intelligent life, signals, structures, atmospheric anomalies shaped by technology, the reaction would be deeper and far more fragile. Entire civilizations could feel their sense of identity dissolve and reform simultaneously. Some would see opportunity, others threat. Some would feel wonder, others fear. Yet no matter the reaction, humanity would know instantly that the universe contains not just life, but minds. Minds that think, dream, build, and question as we do. Even before direct contact, the knowledge alone would challenge our ideas about morality, meaning, and existence. Religions might adapt or fracture. Nations might unite or retreat. Children raised in a post-discovery world would grow up with a fundamentally different worldview, one that sees humanity as part of a cosmic community rather than its center. And yet, beneath the excitement, darker questions would emerge. How does discovering alien life change our sense of security? What if intelligent life is rare, and we are its last surviving remnants? Or worse, what if intelligent life is common but dangerous? The human mind oscillates between awe and fear, hope and caution. Discovering life would magnify that duality. But the most unsettling thought is one scientists quietly whisper long before the public hears it. If we find life, then that life may eventually find us. Even microbial life raises questions. Could spores ride on interstellar dust? Could microbes survive eons and spread from world to world? Could panspermia connect multiple planets, making life a cosmic phenomenon? But intelligent life triggers deeper anxieties. Would they be peaceful, curious, indifferent, predatory? Would they communicate through light, through physics, through forms we do not yet understand? And if they are more advanced, billions of years older, would they even notice us? Would they interfere? Would they hide? Humans have always reacted to the unknown with a blend of wonder and dread. A distant civilization discovering us first is a scenario that sends chills through even the most optimistic minds. It shifts the power dynamic instantly. It suggests we are not explorers, but the ones being observed. That fear is ancient, evolutionary, rooted in the survival instincts that protected early humans in a dangerous world. Yet, in the context of cosmic discovery, the fear becomes existential. We are a young civilization, loud with radio signals, bright with city lights, careless with our technological signatures. We have been shouting into the darkness for decades without knowing who or what might be listening. So the question is not simply, what if we find life? It becomes, what happens if life finds us first? Would it be contact? A warning? A gift? A disappearance? Or silence? An indifferent universe acknowledging us only with a passing glance? These questions do not diminish the beauty of discovering life. They deepen it. They remind us that life anywhere, even in its simplest form, is a bridge, forging a connection between worlds separated by light years. And there is a softer, quieter emotional layer to this shock: relief. Humanity is lonely. We have spent millennia staring at the stars, sensing that something must be out there. To finally confirm it would fill a void we rarely admit exists. A longing for companionship, for cosmic kinship, for proof that existence extends beyond Earth's fragile shell. Whether comforting or terrifying, the discovery of life would be the most significant moment in human history. It would reshape how we treat our planet, how we imagine our future, how we teach our children, and how we navigate the vast unknown. And all of this, the hope, the fear, the wonder, would unfold because of a simple signal detected on a small planet orbiting a small star 26 light-years away. A signal that whispers, life may not be unique, life may not be rare, life may not be alone. The planet waits in the dark, suspended in the quiet orbit of its small red star, unaware that it has become the focus of distant beings searching for answers. It drifts through the void with no urgency, no purpose, no sense of the monumental implications its existence carries for us. To the universe, it is simply another world among countless others. But to humanity, it has become a symbol, a silent monument to possibility. Section 18 captures this stillness, this sense of anticipation, this feeling that the planet is holding secrets just beyond our reach. Picture the world as it moves along its tight orbital path. On the day side, the red dwarf's muted glow bathes the landscape, if a landscape exists, in dim, copper-tinted light. The skies, thick with vapor or thin as glass, warp the starlight into shifting shades of crimson and gold. Clouds may form in great looping arcs, or they may gather only along the twilight belt where heat meets cold in atmospheric tension. Steam could rise from unseen surfaces, drifting upward into winds driven by the violent contrast between sides. Or perhaps frozen crystals fall in the perpetual darkness of the night side, silently accumulating in places where starlight never touches. The planet is a study in contrasts, a world defined by opposition. Heat battles cold, light battles shadow, atmospheric chaos contends with silent stillness. And somewhere in the midst of those contrasts lie the clues scientists seek. Clues to whether the world is alive, whether oceans lie beneath its clouds, whether chemistry cycles through its atmosphere in patterns that resemble the early Earth. But the planet itself remains indifferent. It reveals only what physics allows and only in fragments. Its story comes to us in spectral whispers rather than spoken truths. From our point of view, the world feels close enough to imagine, yet distant enough to resist understanding. JWST's infrared vision can catch the faintest breath of vapor, but it cannot show us the landscapes that produce it. Simulations paint scenarios of glowing coastlines or steamy oceans, but none of them can confirm what lies beyond the veil of clouds. In a sense, the planet becomes a metaphor for the limits of human knowledge, always glimpsed, never grasped. We see its silhouette, we map its spectrum, we simulate its atmosphere, but we cannot yet touch its truth. There is something haunting about this distance. The planet circles its star in a void filled with silence, unaware of the eyes fixed upon it. Meanwhile, on Earth, millions of people follow its story. Scientists running models, students learning about exoplanets, dreamers imagining alien skies. The planet becomes larger in our imagination than it is in reality. It becomes a canvas for hope, a stage for scientific ambition, a destination for future missions we have not yet built. As the data accumulates, the curiosity surrounding the planet deepens. Every new observation sharpens its outline, but also expands the mystery. New measurements reveal hints of clouds, but not their shape. Variations in the spectral lines suggest atmospheric dynamics, but not their patterns. The more we learn, the more the planet seems to retreat into the darkness, withholding its final answers. It is a world revealed in glimpses, like a figure seen through shifting fog. Perhaps it is this elusiveness that makes the planet so compelling. A fully understood world loses some of its allure, but a partially revealed one draws us forward. This planet feels like a doorway, slightly open, creaking quietly, offering a sliver of what lies inside. Not enough to enter, just enough to entice. Its orbit becomes a clock, marking the intervals between our brief opportunities to look deeper. Each transit is a heartbeat, a reminder that even worlds light years away follow rhythms we can learn to read. And yet, beneath all the scientific fascination, there is an emotional truth. The planet feels alive not because it contains life, but because it contains potential. It reminds us that the universe is not a fixed, empty void, but a dynamic place filled with creation, transformation, and mystery. It shows us that even in the quietest corners of space, worlds can hold possibilities that challenge our understanding of existence. This is why the upcoming observations feel so monumental. The planet seems to be waiting, not actively, but simply by being there, orbiting in darkness while humanity prepares its instruments, refines its models, sharpens its questions. We stand on the edge of insight, staring across light years at a world that does not know we exist. Its silence is powerful, not because it hides anything malicious, but because it invites us to search harder. As we learn more, this planet may prove to be a false lead, too hot, too cold, too volatile, too unstable for life. Or it may prove to be something astonishing, a world with weather systems, a world with oceans, a world with chemistry that hints at biological signatures. The truth may be mundane or extraordinary, but either way, the pursuit will reshape the future of exploration. In this moment, the planet remains poised in cosmic suspense, shrouded in shadow, draped in mystery, carrying traces of water vapor like a quiet signal written into its skies. Whether it is a cradle for life or simply a fascinating anomaly, it stands as a milestone in our search for meaning in the universe. We watch it, we wait for it, we listen to it, and as our instruments grow sharper, the planet continues its silent orbit, patient, enigmatic, waiting in the dark until the day its secrets finally step into the light. Light is more than illumination. It is a messenger, a traveler, a silent archivist carrying the memories of everything it touches. When JWST studies an exoplanet, it does not rely on images or direct views. Instead, it listens to light itself, specifically, to how that light changes color as it filters through an alien atmosphere. This technique, known as spectroscopy, transforms invisible wavelengths into a readable language. Through it, scientists can decode the chemical story of a world they will never physically see, using nothing more than the faintest shifts in starlight. Imagine holding a prism up to a beam of sunlight. The light splits into a rainbow, each color representing a wavelength. Now imagine that same rainbow arriving from a distant star, and a planet drifting between the star and the telescope. As starlight passes through the planet's atmosphere, some wavelengths vanish, absorbed by molecules. Water vapor steals certain bands. Methane takes others. Carbon dioxide carves its own unique notches. Each molecule leaves behind a missing line, like a secret carved into the spectrum. These missing lines are the planet's fingerprint, its chemical signature, invisible to our eyes but unmistakable to a machine built to detect them. JWST's instruments do not see colors the way humans do. To them, light is a coded sequence of peaks and dips, a map of absorption patterns spread across infrared wavelengths. When plotted, the spectrum resembles a mountain range, with valleys carved where molecules have absorbed the light. Scientists scan these features as though examining ancient inscriptions, searching for patterns that align with known molecular signatures. It is a meticulous process, requiring sensitivity capable of detecting changes in brightness smaller than 1 part in 10,000. Yet within those tiny fluctuations lies the identity of an entire atmosphere. Infrared light plays a crucial role in this process. Unlike visible light, which can be stopped by dust or thick clouds, infrared wavelengths slide through obstacles with almost effortless grace. They pass through gases and vapors that would otherwise obscure the truth. This allows JWST to peer into layers of an atmosphere that telescopes before it could never reach. Pounds of gas, droplets of steam, wisps of cloud. Nothing escapes the scrutiny of infrared spectroscopy. It reveals what a planet breathes, how it evolves, what elements shape its climate, and even whether volcanic or chemical processes are at work beneath the clouds. But the true magic of spectroscopy lies in the tension between revelation and mystery. The technique reveals just enough to ignite curiosity, yet never enough to remove all uncertainty. When JWST identifies an absorption feature, it raises further questions. How thick is the atmosphere? Which layer did the light pass through? Were the molecules spread evenly or gathered in clouds? Were they affected by heat, frost, or stellar radiation? Each answer leads to new uncertainties, and each uncertainty pulls scientists deeper into the investigation. The act of reading spectra is like hearing a whisper from across an immense distance. Scientists lean in examining anomalies, dips where none should exist, curves that deviate from expectations, subtle distortions that hint at unknown chemistry. Light behaves with both precision and mischief. Tiny fluctuations could signal the presence of a rare molecule, or they could be nothing more than noise, an echo of the star's surface or a ripple in the telescope's machinery. Interpreting the difference requires experience, intuition, and patience. The complexity of the process becomes even more profound when clouds come into play. Clouds, whether of water, methane, or exotic chemicals, scatter light in unpredictable ways. They can flatten spectra, dilute signals, or mask entire chemical layers beneath a reflective haze. A world covered in clouds might hide oceans beneath them, yet the spectrum would resemble that of a barren, featureless planet. Conversely, a world with thin or patchy clouds might reveal faint hints of molecules that suggest something more dynamic. Spectroscopy becomes a delicate dance between discovery and uncertainty, a battle to extract truth from layers of atmospheric disguise. The exoplanet observed in this case revealed a spectrum filled with tantalizing features. JWST captured the starlight bending through its atmosphere, extracting faint patterns that seemed to align with water vapor signatures. But amidst the clarity were hints of something unexpected. A distortion here, an unusual dip there. Signals that could be clouds or chemical interactions or something more exotic. The spectrum seemed to hold its message tightly, offering glimpses but refusing to fully reveal its secrets. This moment of ambiguity is where the emotional power of spectroscopy lies. The universe rarely gives straightforward answers. Instead, it provides fragments, pieces of a puzzle meant to challenge humanity's hunger for understanding. Each spectral line becomes a narrative thread. Each dip becomes a clue. Each uncertainty becomes an invitation to look again. This tension between knowing and not knowing ignites a sense of wonder that transcends scientific analysis. In the end, spectroscopy does more than analyze the atmospheres of distant worlds. It transforms the universe into something intimate, something we can read, interpret, and emotionally connect with. It turns starlight into language, planets into characters, and cosmic distances into bridges of meaning. Through the prism of spectroscopy, invisible worlds become visible, silent worlds speak, and the universe reveals that even its faintest signals can carry profound truths. And so, the spectrum of this distant exoplanet hangs before us, part revelation, part enigma, challenging us to decipher the message hidden within its shifting colors, urging us deeper into the mystery that surrounds this world in the dark.